At first, we will discuss about the quotient space. Okay, what is quotient space? And then we will discuss is the quotient space is a subspace of vector space P. We will solve this question, and then we will prove that the quotient space is actually a vector space. Okay, so first of all, assume and let V over F be a vector space. So we have a vector space V over F and W be subspace of V. So we have a vector space and we have a subspace of that vector space V. So we collect all those quotient V plus W such that V belongs to capital V. This is set of all quotient. Okay, this is a set of all quotient. Okay, so this will form a vector space with the operation. And what will be the operation? The addition. First operation, we have two operations. First operation is plus and second operation is dot. So first operation we will write here that take any element from S. So first element will be V1 plus W. First element is like this. The element of S will be element of V plus W plus V2 plus W, and this will be V1 plus V2. Okay, V1 plus V2 plus W. The plus operation is defined like this. And dot operation, what is dot operation? In the quotient space which we will prove here, then take any scalar from the field F. So A into V plus take any element from S. This is element of S. This is element of field, and it will be A of V plus W. Okay, this is belongs to S. This is belongs to field. So how we define operation? Okay, we add first vector to this vector v1 plus v2 and we will add w. W is a subspace. Okay, and we will multiply a to b. We know how to multiply because of v is a vector space. Then ab belong into v, so this belong into S obviously, because a is a member of field and v is a element of b, and v is vector space, so it will be closed under a scalar multiplication. So this will belong into capital V, so it will belong into S. Okay, similarly this belong into S because v1 plus v2 will be belong to capital V. So this is the operation we defined on this set. Now we will prove this set will form a vector space with respect to both these operations. Okay, so we will continue. Now we denote it by V by W. Okay, whatever we will get the vector space, we will denote by V by W, means all those element V plus W such that V belong into capital V. Okay, we'll denote this vector space by this notation V by W. Okay, this is the notation, nothing else. Now, is quotient space a subspace of V? First, if V by W means we can write here S equal to V plus W, where V from capital B. If this is a vector space, assume this is a vector space, we have not proved yet, but we will prove. Okay, so this is a vector space. Now is the subspace of V. Okay, here V by W is a vector space over the field F. Okay, over the field F, whatever field is used for V, the same field will be for used for V by W. Okay, this should be noted. Now here what we see that element of V by W is the V plus W, and V plus W means V plus W and W belongs to capital W. This is the subset of V. Okay, element of this vector space is the subset of V. So this element of V, element of S equal to V by W, does not belong into V, because this is the subset, not an element. So will not belong to V. This will imply, because a element of S does not belong into capital V, so collection of these elements will not be subset. So S is not a subset of V. Okay, because one element is a subset of B, then collection of all the element will not be subset of B. This will be the maybe subset of power set. That concept can be here, power set of B. Okay, so this is not a subset. Since it is not a subset, so we cannot, it will not be a subspace. So it will not be subspace. Okay, so, so everything should be clear. And if is there any doubt, please ask in the comment box, and never forget to subscribe my channel. Okay, that motivates me. Okay, now we will prove this statement that V by W equal to V plus W, where V belongs to capital B, is a vector space. So we will prove that it is a vector space. So इसे वेक्टर स्पेस प्रूव करने के लिए हम लोग को क्या प्रूव करना पड़ेगा? फर्स्ट में नीड टू प्रूव what we need to prove that first, with respect to plus V by W is an abelian group. Okay, so this should be abelian group. So first it will be group, and due to commutative it will be abelian okay group. So first we should pick, so we should have closeness. Take two element, let V1 plus W and V2 plus W belongs to capital V by W. We have taken two element, and if you add V1 plus W operations and V2 plus W, what it will be? We have defined the operation like we will add V1 to V2, so it will be V1 plus V2 and then add W. Now this is capital V, because V1 and V2 are member of capital V. Okay, how we define the element of S or V by W? So it will belongs to V by W, and say it is closed. Okay, so we have closeness with respect to first operation. Second, we need to have associativity. So take three element. Let v1 plus w comma v2 plus w comma v3 plus w belongs to v by w, and we will show the associative, and v1 plus w, okay, and we will add v2 plus w to v3 plus w. Okay, so what we got here, that v1 plus w plus, now we will do first operation here, then it will be equal to how we add two elements of v by w. This is the element of v by w, this is the element of v by w, and we add the v2 plus v3, v2 plus v3 plus w. Okay, that's the definition of addition using definition of addition. Now this will be equal to, now we can add this belonging to v by w, this whole terms belonging to v by w. Okay, so we can write here v1 plus v2 plus v3 plus w, because this element belonging to v and this element belonging to v, so we will add v1 to v2 plus v3, what we did here, plus w. Now since this v1, v2 and v3 belongs to capital V, and v capital V is a vector space, so it will be associative. Okay, v1, v2 and v3 should have associative property because this belonging to capital V. So we can write here v1 plus v2 plus v3 plus w. Okay, and this can also be written as v1 plus v2 plus w, okay, plus v3 plus w. Okay, if we add again, then we will similarly get v1 plus v2 plus v3 and plus w, and so we can have here v1 plus w plus v2 plus w plus v3 plus w. So similarly, if we add these terms, we will get this term, because v1 plus v2 we will add, and then again add w, and this is the same as this one. So we can see here that we have proved the associative. We have added first two last element to first element, and here we have added first two element to last element. Okay, so we have associative. Third, we should have identity element. So if we take E equal to W, so what the identity element behaves, that's any element add, we will add, from that we will get same element. So this should be V plus W. Okay, we are using W as a identity element. So how we can add V plus W plus, we can write 0 plus W. Okay, and now this is LHS, and what we will how we add here, so V plus 0 plus W by definition of plus, and V plus 0 because 0 is the identity element of V, 0 is the identity element of vector space V, so it will be V plus W. So we got that, and see W is an identity element. Now we should have an inverse. Okay, so take any element v plus w and take minus v plus w. So we can show easily that this element is in the inverse of this element. Okay, so they are both are inverse of each other. So if we add, we should have identity element. If we add this element and this element, and what is the identity element? Identity element is w. So we should get w only. So if we add v plus w, this is an arbitrary element of capital V by w. Let this one. So if we add this plus minus v plus w, so it will be v minus v plus w, and this will be v minus v0 plus w, and 0 plus w equal to w. What we get? An identity element. An identity element. Okay, so we have an identity element, we have an inverse element. Now we should have commutative with respect to plus. So take any element v1 plus w belonging to capital V by w, and v2 plus w belongs to capital V by w. Now we will prove that it follows commutativity property. So add v1 plus w to v2 plus w. What we got here? v1 plus v2 plus w. How we got here? We have used only the definition of vectors, definition of plus. Okay, this is the definition of plus, that we will add v1 to v2 and then w. Okay, now we have v2 plus v1 plus w. यह हमने कैसे किया? बिकॉज v एक वेक्टर स्पेस था, कैपिटल V एक वेक्टर स्पेस था, और ये दोनों एलिमेंट v1 एंड v2 इसी वेक्टर स्पेस से है. सो सिंस वेक्टर स्पेस में abelian properties means abelian, that should be abelian with respect to plus. So ये प्लस के रेस्पेक्ट में abelian ग्रुप होगा, इसीलिए we can commute them. Okay, so that's why we have written here v2 plus v1. So we can have v2 plus w plus v1 plus w. Okay, so we have associative properties. Okay, for any element we have taken any arbitrary element. This will imply v by w is an abelian group. Okay, now further property we will prove that 1 dot x means v plus w, and v plus w, let v plus w be any element of v by w, and this will be v plus w. Okay, we will prove here. This should have. So what is LHS here? 1 dot v plus w. And how we define dot, we can see here how we define dot. So okay, we have defined dot here for any field member, and we have any element of S, means element of v by w. So we have multiplied a to v plus w. Okay, so similar manner we will do here. So it will be 1 into v plus w, and 1 into v is v plus w. We know that. So how we got is RHS. Now further properties we have to prove that let v1 plus w belongs to v by w, and v2 plus w belongs to v by w. Okay, so now we have to prove that v1 8 into v1 plus w plus v2 plus w equal to a to v1 plus w plus a to v2 plus w. That's the distributive properties only. Okay. Okay, if we expand LHS, we can get easily this one. So if we will apply the higher definition of addition first, so we got v1 plus v2 plus w. Okay, this is w. And now use the definition of dot here. What will be definition? A dot v1 plus v2 plus w. And since v is the vector space, we have distributive properties for this element, so we can write a v1 plus a v2 plus w. Okay, and now this can be written as a v1 plus w plus a v2 plus w. Okay, and so further we can have a v1 plus w plus a v2 plus w. Using the definition of dot, we will get this one. Using definition of dot, we will get this one. Okay, similar manner, one can prove that a plus b, here a belongs to field. Okay, so this property, let a b belongs to field and v plus v by sorry v plus w belongs to v by w. So one can prove easily that a plus b into v plus w equal to a v plus w plus b v plus w. One can easily prove this statement using the definition of dot and definition of plus. Okay. Now we will prove the last property for the vector space is that let a b belongs to field and take any element v plus w belonging to capital V by w. So what we proved that a b dot v plus w equal to a b v plus w. Okay, that's associativity in multiplication. So we can have all this can be proved easily that we will use the definition of multiplication first. So it will be a b v plus w. Okay, and now since a b belonging to field and v belonging to vector space, so we can have a b v plus w. And now use the definition of dot, so b v plus w. Okay, because if we multiply this field member to this element, we will get same here. Okay, and this can also be written as a to v, v plus b, again using the dot operation between these element. Okay, so we can get here equal to RHS and say v by w is a vector space. Okay,